Okay, our drug is olaparib. The brand name is Lombardi. What is the primary cause of cancer? Yes, Jackie.
Mutations.
Correct. Mutations cause cancer. We have learned this pretty much all semester, right? What our drug does is use this DNA damage to kill cancer.
Alright, so just some basic information about our drug. It was FDA approved December 2014 and was developed by the company Pantheon Pharmaceuticals. So an important thing to take note of for our drug is it's a PARP inhibitor and is only given to patients with a mutated BRCA1 or 2 gene. And it is usually given after multiple rounds of chemotherapy. Okay, so quickly before I go into the cancer, it's important to know that normal cells have two mechanisms for repairing broken DNA. PARP, which is an enzyme, and BRCA1 or BRCA2 genes that are similar, but the main difference between the two is they both are meant to code for proteins that work in different parts of repairing DNA. So in our cancer, BRCA1 deficient ovarian cancer, it is for when people have a mutated BRCA1, a loss of function mutation, and BRCA1 is no longer present in normal cells.
Yeah, so this BRCA1 gene codes for an enzyme which repairs DNA. PARP is also an enzyme which repairs DNA. And in this specific cancer, which our drug is designed for, the BRCA enzyme is not present at all. Alright, so how does olaparib inhibit PARP? So normally when PARP is repairing damaged DNA, it binds to the DNA and then moves along as it repairs it. What olaparib does is it binds to a specific part of PARP so that when PARP binds to the DNA, it can't move. So it's stuck and can't fix the DNA. Does that make sense? Any questions?
And so this is what makes olaparib so revolutionary. It specifically only targets cancer cells because with this mechanism, in the cancer cells, there will be inhibited PARP because of the drug, and there will be no functioning BRCA because of the loss of function mutation. But in the healthy cells, there will be inhibited PARP because of the drug, but the BRCA will still be there to fix the DNA damage. And so as you can see on this graph, we have inhibited PARP, DNA damage, and then the cancer cells die from an accumulation of DNA damage that they cannot repair, but the normal cells continue fixing their DNA breaks.
So, just put simply, right? PARP is stopped in all cells, right? BRCA deficiency is only in cancer cells, so normal cells still have the BRCA enzyme. So normal cells without PARP but still have the BRCA enzyme can survive because they can still repair their DNA, but because the cancer cells don't have either, it can't survive.
Any questions?
Does the inhibited PARP have any other side effects on the healthy cell?
No, that's where our drug really comes into effect. A big part of it is because BRCA1 is already present in healthy cells, it only takes effects on cancer cells since both mechanisms of DNA repair are gone.
Jason?
So you can have BRCA1 normal in normal cells and mutated in cancer cells?
Yes.
Yes.
Can DNA still replicate in the cancer cells? They are damaged, but can they still be replicated?
Yes.
Kind of to go off of Lou, I don't know if this is a dumb question, but like cancers are based off of mutations, right? So like why would they kill off the cell if, as a result of like not damaged?
Well, like,
damaged DNA as in like not mutation.
Like
Sorry.
yeah, like more physical breaks.
Okay, physical breaks. Okay.
Like a literal break on the graph,
Okay, sorry.
single strand DNA breaks or double strand DNA breaks.
But it's important to realize that the cancer isn't causing the cancer cell to die, right?
It's the lack.
It's the lack of PARP, right?
It's the lack of the ability to fix what
Yeah,
it needs
okay.
to fix. So data of mechanism. In this experiment, what scientists looked at was how efficiently olaparib actually inhibited the PARP enzyme. So what they did, basically, they took a bunch of cells and then introduced the drug to them and monitored in a course of 5 minutes what happened to the levels of PARP enzymatic activity. And so, because it's hard to measure activity, what they did is they looked at PAR, a protein which forms as a result of PARP enzyme activation. So basically, the more PARP protein you can deduce, there was more percentage PARP enzymatic activity to have created those proteins. And so looking at this graph, you can see a sharp decline of PARP activity as a result of more olaparib being introduced into the cells. So basically this just means that more of the drug means less PARP enzymatic activity. So olaparib effectively inhibits this enzyme. Is that clear?
Yeah. All right. So the efficacy. So the y-axis in this graph is the tumor volume, so how big the tumor is, and the x is the time of days. So the black is the control. As expected, the tumor size increased over time because it wasn't being treated with anything. The blue is cisplatin, which is a common chemotherapy drug for ovarian cancer. And as you can see, the tumor size decreased, but then increased after around 40 days. The green is our drug, olaparib, which stemmed the tumor growth after around 15 days. And the red is olaparib and cisplatin combined, which decreased the tumor volume almost immediately and stayed low through the rest of the study.
And all of this data was taken from mice who had this BRCA-mutated cancer. So what can you conclude from this? That olaparib alone is more effective in treating the cancer and shrinking tumor size than standard chemotherapy drugs currently being used, but that the combination of the chemotherapy drug and olaparib was most effective. And so you might ask yourself, why is this? This is because chemotherapy causes significant DNA damage that at a much quicker rate than it would naturally occur. So basically, there's more damage for the cancer cells to not be able to repair, so they would die off quicker at a higher rate.
Right, so that goes back to our chart from before, right? Increased DNA damage, and the PARP can't fix it, so they work in tandem in the cancer cell. Questions?
Anyone got it?
So basically, when a cell is treated with chemotherapy, there's more opportunity for DNA damage, so there's more opportunity for your drug to work.
Correct.
Yes.
So would this work in so BRCA1 is, like you said, an enzyme that people can get mutations in, right? So there are people that have BRCA1 mutations. So would this work if they didn't have a functioning BRCA1 or 2?
You mean like if their whole body didn't?
Correct.
Then no. It would not be designed for that. It would only be designed for this specific ovarian cancer.
But it would have to be
Oh, right, this is-
tumors that develop that
Right,
mutation.
right, right.
Yeah,
It's
yeah.
not a systemic.
Yes.
So this that you said this is specifically for BRCA positive.
Yes.
Right. Okay.
Okay, so like any treatment, olaparib has its side effects. They can range from mild symptoms like coughing or nausea. However, it has been recorded for more severe symptoms like the red ostricula myelodysplastic syndrome, which is a bone marrow disease for the body. However, despite this, there was a trial done in 137 patients with BRCA-mutated cancers that were treated with chemotherapy and afterwards olaparib. And after the trial was over, they saw that these patients had an ECOG status of 0 or 1. Now, ECOG status is a scale from 0 to 5 on how well a person can still carry out normal everyday activities after they've been infected with the disease. And 0 or 1 are the two lowest ones, and the lowest you have is the better. And 0 would be considered you'd be able to do everything you were able to do before you got the disease without any consequences.
You know, this study was in humans.
This
This
is
was
the
in
scale.
This is you.
It's like youth. It's like
107 patients.
Yeah. That was you.
That's it.
The mice couldn't carry out their
Yeah.
daily lives as well as they had
Like,
previously.
what if it's just like walking around in a
Yeah, no, I get it.
Yeah.
I'm supporting that.
Is this human feedback, so they grade how how their life has changed, or is this their tests?
No, this is specifically asking the patients in the study.
Do you know how they measure the EC regime by any chance? You might
Well,
not.
that's just like the patients. It's not data. It's physically asking the patients how they're feeling.
Oh, like a
Yeah.
survey type
Yeah.
thing? Okay,
And so this percentage was only made possible because of olaparib's ability to specifically target cancer cells. And surrounding healthy cells are not affected, contrasting the effects of current chemotherapy. So why does this matter? Although ovarian cancer is fairly rare, as soon as there are signs of this BRCA mutation, the risk jumps to about 50%, and about half of diagnosed patients die. Not only does olaparib provide promise for treating this very serious disease, it also opens up the field to a whole new class of cancer therapy drugs, PARP inhibitors. Olaparib itself is already being tested in pancreatic, gastric, and even breast cancers.
Just to clarify that, those cancers are all BAC deficient. So the main facet of our drug is that it does not physically fight cancer like chemotherapy or other traditional mechanisms do. What it does is it forces cancer to fight itself. That's all we got.
So, do you think for cells that have an impairment in detecting DNA damage or pushing cells towards apoptosis because of that, do you think that would change the efficacy of your drug, or does it override that?
I mean, it has to be assumed that would affect it somehow, but I mean that'd be hard to measure because I mean the mutations are going to be happening so frequently. But I think that'd be important to test. Right? We just didn't look into that.
Any other questions? No?